Okay. Hi, everyone. Welcome to this wonderful event. Let me start off by taking the opportunity to thank John and the rest of the team for organizing such a great event. I want to tell you about this recent work that I had with wonderful collaborators from the Ethereum Foundation, Dimitri and Lev. So I guess I'm supposed to introduce myself. So I'm Ron Rothblum. I'm a professor at the Technion, and this year on sabbatical at Succinct. I'm in the business of proving true stuff, but in this work, we're going to be proving something false. But actually, we'll get to it at the end of the talk. I want to encourage others to also try to prove false stuff. So we'll see. Yeah, so we're going to be talking about Fiat-Shamir, which I assume that most, if not all of you, are familiar with. But we'll kind of describe it quickly just to remind ourselves. So it's this amazing work by Amos Fiat and Fiat-Shamir from the 80s. And in a nutshell, the Fiat-Shamir transform is this kind of incredible way to transform interactive protocols into protocols that are non-interactive. And this turns out to be very, very important and remarkable. We'll talk about why. But especially in the context of this conference, the Fiat-Shamir transform is a critical component in most, if not all, but almost all snark constructions. So it's very important. I should say that I don't think that Amos and Adi had in mind snarks when they were developing it. So the original transformation was geared around building efficient signature schemes, and it's still used for that. But nowadays, it's being used much, much more broadly. OK, so this is the Fiat-Shamir transform. So how does it work? So in the Fiat-Shamir transform, we start off with an interactive argument system. So there's some protocol for proving correctness of a computation, and it's highly interactive. One catch is that the protocol has to be of the public coin variant, which means that everything that the verifier sends are just random coin tosses. Okay, so we have an interactive protocol here on the left-hand side. So the prover sends some messages we'll denote by alpha, and the verifier responds with messages which we'll denote by beta. And again, the betas are necessarily just random coin tosses. And if you think, the fact that we're restricting to these public coin protocols in which the verifier only sends random coins, turns out that the actual interactive protocols that we care about are of this form. So that's why we're going to be focusing on them. The idea in the Fiat-Shamir transform, again, is to transform these interactive protocols to be non-interactive. And the key idea, loosely speaking, is basically to replace the verifier with a hash function. So we're going to be using a hash function h. And we're trying to emulate the interactive protocol. So the prover can generate its first message, alpha1, easy peasy, no problem. Now it's sort of supposed to wait for the message from the verifier. Instead of, we don't want interaction, so it cannot wait for it. Instead, we'll derive this message by hashing the prover's message, alpha1. And we'll basically hash everything else that we can. Okay, so x is some statement on which we're proving correctness. So we also include x in the hash. Now that we know what beta1 is, we can generate alpha2, send it over. And now we'll similarly generate beta2 as a hash of alpha1 and alpha2, and so on and so forth. We can keep generating the verifier randomness by just applying the hash function. And overall, we can now send the entire sequence of alphas over to the verifier and run the previous verification algorithm. So it's a very simple transformation. I should say, though, that despite its simplicity, there have been a lot of attacks on Fiat-Shamir, and I would say that these are attacks on the implementation. So while it's simple to describe in a slide, it turned out to be quite tricky to do in code. Basically, oftentimes you have different components in your proof system that are sending things over, and it's easy to forget to include some stuff in the hash, and this has led to sort of critical breaks. In contrast, and jumping ahead in the talk, the attack that we described today is not against a particular implementation bug. It's really against the transformation as described, and as you sort of were supposed to do it until we realized that it's problematic. Okay? So Fiat-Shamir, extremely influential, extremely important. Just to highlight some reasons, it's incredibly powerful because it seems like interaction buys us a lot. A lot of the protocols that we really, really care about, so things like Fry or SumCheck or GKR, bulletproofs, all of them are highly interactive, and it seems the interaction really, really helps. But on the other hand, interaction is often problematic in practice, and the Fiat-Shamir says, hey, you can design these things to be interactive, but then not pay for it, so everything can be non-interactive. So it's extremely powerful. Another thing that's remarkable and doesn't always happen in cryptography is that it's very cheap, it's very practical. All you need is a good hash function. So it's very lightweight, no like fancy public key operations, very lightweight. And it's extremely useful. Back in the 80s and 90s, and still today, we're using Fiat-Shamir to build efficient signature schemes. It moved on kind of more in the theory literature to build CS proofs, which have sort of evolved into these like snarks and starks and so on. So incredibly powerful. Cool, so it's great. We really like it and it's really important. The question is kind of that we're focusing on today, does it work? Okay, so is this methodology sound? And I want to start with, just like at the level of intuition, it's very clear why it feels like it should be sound, right? So when you do Fiat-Shamir, to generate the message beta 1, the verifier's message, the prover sort of has to decide what alpha 1 is and apply the hash, right? So you have to it seems like you have to decide what alpha 1 is, and only then you get to know beta 1, which is exactly what happens in the interactive protocol. So it seems to be kind of a good emulation of what happens interactively, making this be reasonable. As cryptographers, we're not so happy with things just being reasonable. We would like something beyond that. And we have this work by Poincheval and Stern from the 90s. What they showed is that if you model the hash function that you use in an idealized way as a random oracle, so basically you choose the function at random from all functions, then this thing provably works. The catch is that we can't actually use totally random hash functions. It's way too expensive to even think about. So the common heuristic is to design the protocol and analyze it in the random oracle model. And indeed, it works for Fiat-Shamir. And the common interpretation is, if you started off with a secure interactive protocol, you compiled it using Fiat-Shamir, then we know that the resulting protocol is secure in the random oracle model. Now, if you replace the random oracle with a concrete hash function, if there is an attack, it seems like this should indicate a weakness in the hash function. And we should just switch to a different hash. Right? Make sense? OK, so it's a very natural interpretation. But this interpretation was challenged in a beautiful work about 20 years ago, a paper called The Random Oracle Methodology Revisited. It's by Ran Canetti, Oded Goldreich, and Shai Halevi, who showed the following remarkable fact. So they constructed some particular cryptographic schemes and proved that they are secure in the random oracle model. But what they also showed is that if you take these schemes and replace the random oracle by any hash function, no matter what, the resulting scheme is broken. Okay, so it's definitely not a fault of the specific hash function, because no matter what hash function you use, their scheme is broken. The catch, however, is that specific schemes that they constructed were highly contrived. So what does it mean to be contrived? In particular, it means that they were intentionally designed and built in order to fail in this way. Okay? So this is a beautiful work by CGH, Canetti, Goldreich, and Halevi. A follow-up work by Boaz Barak and by Shafi Goldwasser and Yael Kalai showed that actually things are more worrying. So actually even Fiat-Shamir itself is broken in a similar way. So what Yael and Shafi showed was an interactive protocol, so Boaz, an interactive protocol that is secure, it's sound. When you apply Fiat-Shamir by Poincheval Stern, the resulting protocol is secure in the random oracle model. But now, for this Fiat-Shamir, if you replace the random oracle with any concrete hash function, it's broken. The catch here is that the interactive protocol that you start off with is contrived. Again, it was designed in order to fail. Still, it's kind of getting closer. And a few years ago, together with Bertusek, Bronfman, Holmgren, and Fermi Ma, we showed that actually, for the specific way that we build hash-based snarks, namely take an IOP and compile it using a vector commitment or a Merkle tree, however you want to think of it. Even for that specific thing, which is a very common construction of snarks, we have a similar attack. So even that is broken. What's the catch here? Well, either the IOP or the vector commitment that you use for this result needed to be contrived. Okay, so we still had the contrived component. It was just kind of becoming smaller and smaller. But still, for all of these results, there was some contrived component, which I think was a reason that people were not very worried about this line of work. Okay? And what I want to show you today in this work is that we actually have demonstrated an attack against a particular standard, natural, and popular protocol that is being used in practice. And we show that you can do an attack of this flavor on Fiat-Shamir of this protocol. So that's what I'll show you today. What does it mean to attack? I'll say it more precisely, but basically we'll be able to convince the verifier to accept a statement even though the statement is blatantly false. Okay? Cool, so I want to show you the protocol that we attack. In order to do so, I need a tiny bit of background. I'll try to be brief. So we're basically going to need two components. One component is what's known as a polynomial commitment scheme, or PCS. Okay, so I'll explain what that means, specifically of the multilinear kind, but don't worry about it. And the second thing is the GKR protocol. So I want to describe both of them kind of briefly. So let's start off with what is a PCS. So a PCS is basically a way to commit to you have a very, very large polynomial. You can commit to it using a very short hash. And later on, you're able to prove, so you commit to this polynomial P, and later on you can prove statements of like evaluation statements. So P of X is equal to Y. So you can prove these kind of statements using a very short and efficiently verifiable proof. Okay? So thankfully, in this talk, we're just breaking security, so I don't need to define what it actually means for a PCS to be secure. But intuitively, you understand what I mean, right? You hash. You should not be, once you hash, you're intuitively committed to a polynomial, and you cannot open it in different ways. Okay? So that's a PCS. In the talk today, I'm going to be focusing on a multilinear PCS, which basically means that the polynomials that we consider are multivariate polynomials that have degree 1 in each variable. But to be honest, it's not that important. So if you're less familiar with multilinear polynomials, just think of your nice univariate polynomials, and you'll mostly be fine throughout the talk. Okay, so that's a PCS. The second component we need is the GKR protocol. So this is by Yael Kalai, Shafi Goldwasser, and Guy Rothblum, who's also my brother for those who don't know. So the GKR protocol is pretty old by now, so over 15 years old. So it's an interactive proof, which is statistically sound, meaning that secure even against an unbounded cheating prover. And it lets you prove statements of the form C of X is equal to Y, where C is a bounded depth arithmetic circuit. Okay, so we have a bounded depth arithmetic circuit C, and we can prove its evaluation. Something I want to sort of emphasize, in contrast to what we're used to with snarks and so on, here there's no witness in the background. So we're proving C of X is equal to Y. This is in contrast to things you might be more familiar with, which we would like to do, which is, prove that there exists a witness W such that C of XW is equal to Y. And we'll talk more about that later. But for the GKR protocol, we're talking about deterministic computation, just C of X equal to Y. And again, C is a bounded depth arithmetic circuit. We'll denote its depth by D. Okay? So how does the GKR protocol work? Or rather, before how the protocol works, what is a circuit? So a circuit is this graph. So you have a graph. The vertices are labeled by either addition or multiplication gates over some finite field on which we're operating. And my circuit is going from bottom up. So you feed in an input, X, and you evaluate the circuit in the natural way. So there is some wiring. So you have arrows saying what goes where. And you all know how to evaluate a circuit. You just apply the gates. Right? So I didn't draw all the wires, but you do this computation until eventually you get an output Y. Right? And we're thinking about a circuit that has a bounded depth, so the depth is not too large. Right? So that's how you compute the circuit. Now, what the GKR protocol allows you to do is prove that you did this evaluation correctly. So I'm coming along and claiming to you that C of X is equal to a value Y. So these last vertices on the top contain a vector Y, let's say, or a string Y. And I want to prove it to you. The way that GKR works is that, in our head, we're going to be thinking of, you evaluate the circuit. Each layer of gates now has an associated value that it got in this evaluation. And we're going to be thinking in our head about taking these values and encoding them in a particular way. So these yellow bars that extend to the right are some particular encoding of the values that we got when we evaluated the circuit. And more specifically, this encoding it will sound complicated, but It's not so complicated, but it's basically taking the values that you see and interpolating them as a multilinear polynomial. This is sometimes known as a multilinear extension. Okay, so this is the values that we see in these yellow bars. Cool, so far we only think of them. We haven't done anything with them. How do you prove, how do you verify? So we start off with the claim that the output layer contains a string y. The first thing that the verifier is going to do is choose a random coordinate in the encoding and compute so there's a claimed output y. We'll compute the value, so the encoding I denote by y hat, and we'll compute y hat at position r. Kind of turns out that that is something easy that you can do. If you know y, it's easy to compute the encoding at the location r. And something to notice is that if a prover was not nice, like the one that we have today, and was trying to fool you, and it gave an incorrect string y prime, then due to properties of polynomials not liking each other, so polynomials are good error correcting codes and have distance, with high probability, if you start off with a false claim about y, then you will have a false claim about the encoding. Okay, cool, so that's what the verifier did by itself. Now what we'll do is we're going to run some sort of interactive reduction protocol that reduces a claim about the output layer to a similar claim about one layer below it. Okay, so now we get a claim about one layer below it. Now we run this interactive reduction step again, and again, and again, until eventually we get a claim about the input layer. Okay, I'm not going to describe how this interactive reduction protocol works, but it's basically based on the sum check protocol, which you probably heard about. Cool, now that we have a claim about the input layer, recall that the verifier knows the input, so it can compute, similarly to how it computed the encoding of the output, it can compute the encoding of the input. And now just check that the value that it got is correct. So that, at a high level, is the GKR protocol. Okay? The main thing to remember from this entire slide is the random point that we chose in the output layer. Okay. So GKR it's a great protocol, but it's still restricted. As I said before, you can't prove stuff like, I have a witness showing stuff. So if you want to prove, here is a hash value that is a hash of a blockchain that has some particular properties, you cannot do it directly using GKR. Rather, you might want to use this protocol that I want to present. So it's a way to build a succinct argument for what we call non-deterministic computations, basically computations in which there is a witness, with the proof length is going to be much, much, much shorter than the witness size. Okay? And the way we'll do it is to combine the GKR protocol with our PCS, so the two components that we have. So here's the protocol and how I want you to think of it. So the protocol is actually going to have two phases. So it have an initial sort of setup phase or pre-processing, in which depends only on the circuit that we're talking about and not yet about the input and output. Okay? So what we'll do first in this step is, the verifier is going to tell the prover, hey, Mr. Prover, here is the PCS, the polynomial commitment scheme that we're going to use. So in particular, if it has a key or a salt or something, then that is specified. And next step, they agree on what circuit we're going to be proving stuff. Now you might think, in typical application, it's the verifier that's choosing the circuit, but especially if we want to talk about soundness, then we want soundness even for circuits that are not necessarily chosen by the verifier, so I'm denoting it as the prover chooses the circuit. Okay? So that's sort of a setup phase, and eventually we're going to have an online phase that will depend on the circuit being proved, but the circuit being proved is very, very large. So the verifier doesn't want to keep it entirely, so it's only going to save some sort of digest that describes the circuit. So a good way to think of it is some sort of hash of the circuit topology. Okay, so it says what's the wiring and what gates you have and so on. Okay, so I'll denote this by bracket C. It's a short description or digest of the entire circuit. Cool, so this is the pre-processing step. Now in the online step, we actually have particular input X that we care about and a witness W. How does the prover prove? Well, first of all, it actually performs the computation. It computes and generates Y. And it's going to take the witness W and hash it using the PCS. So it's committing to W as what I like to call it the guts of a multilinear polynomial. Okay? Cool. So we send over, hey, Mr. Verifier, here is the input X, here's the claimed output Y, and here is a hash of the witness. And at this point, the verifier is going to start running the GKR protocol. So remember what was the first step in the GKR protocol? It was choosing a random point in the output encoding. So that's what we'll do. So verifier chooses a random point in the encoding of y and computes this y hat of r. And now we continue in GKR. So we tell the prover, here is the random point r that we chose. And now we start these like interactive reduction steps, one at a time, until eventually we get a claim about the encoding of the input. Now, in our case, the input is sort of a concatenation of the actual input x and the witness w. And we have a claim about its encoding. Turns out that it's not hard to decompose this claim into a separate claim about x and a separate claim about w. So that's what we'll do. Now, the claim about x, the verifier can check by herself because she has x. So you can check this by yourself. And regarding w, we don't have w. That's kind of the catch. But thankfully, we have a PCS encoding of w. So using the PCS encoding of w exactly lets us check claims of the form the encoding of w at the point that we have is equal to a value. Okay, does this make sense? So this is going to be the protocol that we're interested in going to focus on. Yeah. Hey. Go for it. Yeah, so that's hidden inside the digest C. So it's commitments to these functions.
Right, so how is it, it's running the GKR?
Yeah, so internally within GKR, you'll need to evaluate these things, and the prover is going to help you out. All right, so that's how it's done. Does it make sense? So you commit to these functions, right? That's what the digest C is.
So it has a PCS commitment.
Yes, that's also happening there. Or, if your circuit is nice enough in which you can compute these things by yourself, that's also fine.
Sorry, guys, one technicality. If you have a question, please wait for someone to give you a mic so everyone can hear you guys and also on the streaming. Thank you.
Okay. Yeah. Cool. So this is the protocol that we're going to be focusing on. I'll denote it by pi, and it depends, or parameterized by the PCS what we're using, and the depth D of the circuit on which we're running GKR. Okay? So this is the protocol that we're interested in. What happens when you apply Fiat-Shamir? You replace the verifier by a hash function. So let's see what happens. So same thing as before for the pre-processing step, except that now we also sort of need to set up a Fiat-Shamir hash function. So hopefully it has like a key or a salt or something, so you need to specify what it is. So that's H. Now, in the online step, as before, run the circuit, get Y, hash the witness, get alpha, send them over to the verifier. At this point, the verifier is supposed to choose this random point in the output encoding, but we're not going to wait for the verifier to toss coins and send them over. Rather, Fiat-Shamir tells us just hash everything you know, right? So rather than choosing R at random, we just hash what we know, which is the circuit digest C, the claimed input, the input X, the claimed output Y, and the hash alpha. Okay, so using that, we derive R. The nice thing about the Fiat-Shamir is that the prover can similarly compute R without any interaction. And now they can start running the actual interactive step of GKR, but also here we'll apply internally Fiat-Shamir. So all of the internal random coin tosses that we didn't talk about so much, but that happen internally in GKR are going to be done using Fiat-Shamir. Eventually we get a claim about the encoding of X and encoding of W. The claim about X you check directly, and the claim about W you do using the PCS evaluation. If your PCS is by itself interactive, you're also doing Fiat-Shamir to that. Okay, so this is what the protocol looks like when you apply Fiat-Shamir to it. And we'll denote it by Fs sub H. H is the Fiat-Shamir hash function of the previous protocol. Okay, so this is the protocol that we want to attack. And this is the notation. Something I want to highlight is that this protocol is popular. It's been used in a bunch of works. I think it was not designed in order to be broken. I think it was designed to be safe. So that's in contrast to the previous contrived works. And it's a very natural one. It's sort of what feels like you should do. So it's been used in a lot of papers. And there are also deployed protocols, in particular, Expander by Polyhedra is a popular one that uses this protocol. Okay, so Expander is a GKR-based proof system, and this is the bug fix, the PR after we notify them of the attack. We'll discuss later on what exactly fix means here. Okay, but again, to emphasize that this is very relevant to actual deployed protocols. Cool, so with that setup, I can state what our results are. So what we show more precisely is the following. So tell me what PCS you use. You choose it. Tell me what Fiat-Shamir hash function you use, Poseidon, whatever you want. When you tell me the PCS in H, now for a sufficiently large depth, I can prove a false statement. Okay, so the order of quantifiers is sort of like the depth depends on your choice of PCS and H. What does it mean that you can prove a false statement? So we're breaking what's known as adaptive soundness, which is a very realistic scenario. Essentially what we show is that given, if you tell me what the PCS you're using is and what hash function you're using for Fiat-Shamir, I can generate an explicit circuit C star. We're going to see it today. So it's a circuit C star. This circuit actually won't even have an input X. It would only get the witness W. And I'm going to construct some claimed output Y star and a proof pi. And it's going to have two properties. One is that this circuit, no matter what witness you feed into it, it will never, ever, ever output Y star. So the claim that there exists a W so that C star outputs Y star is just false. It's not true. But nevertheless, we're going to be able to convince our verifier that this claim is true, thereby proving a false statement. Okay? Something that people are often ask themselves, I think naturally at this point in the talk, is how weird does the circuit C star look? Have we pushed the contrived aspect into the circuit? Somehow it seems like, given the way I'm presenting it, it seems like that's what's going on. And in a sense, it is what's going on. But in hindsight, I would say that the circuit C star is actually not contrived, and it's very natural. And we'll talk about that more later on. Okay? Okay. Cool. So I'll also mention briefly two extensions of the main result, but really we'll focus on the previous one. Second main result that I'll mention briefly is that even if you're considering some other circuit C, which looks nothing like my circuit C star, we show an extension of the attack. So there's a way to take your favorite circuit C that you're interested in, and I can modify it in a way that will construct a new circuit that computes the exact same functionality as the circuit that you care about. So exact same input-output behavior. But for this new circuit that I've constructed, I can prove anything I want. In particular, today I like to prove false stuff, so I'll do that. So yeah, I'll go over this briefly. Another thing, we also show variants of our attack that are non-adaptive. So in the sense that we can attack circuits that actually don't depend and don't have inside implementations of the PCS or hash function H. So that's what's known as a non-adaptive attack. We do need to know an upper bound on the sizes of the PCS and hash function H, but nothing beyond that. However, there are some caveats here. The attacks are, for the non-adaptive case, are either less practical or require something non-trivial from your PCS to satisfy, which some PCSs do and some don't. Okay, but this is a version of a non-adaptive attack that we also have. Cool, but today really I want to focus on the first result, which is just showing an explicit circuit for which we can prove something false. Right, so what are we going to do? Again, build a circuit C star, never, ever, ever outputs Y star. Y star, I can already tell you, it's going to be a string of length 2, which is exactly the 0, 0 string. Okay, so Y star from here to the rest of the talk is just a string 0, 0. Okay, so we're going to construct a circuit that never, ever, ever outputs 0, 0, but we'll be able to convince our verifier that it actually sometimes does. Okay. Just to highlight that in this context of an adaptive attack, our circuit C star that we construct, for which we prove this, is allowed to depend on our choice of PCS and hash function H, and indeed it will. Okay, this is an adaptive attack. So what's the idea? At a high level, what we're going to try to do is to have our circuit C star try to predict the Fiat-Shamir randomness, and specifically the point R in the output layer that we were talking about before. Okay, once our circuit predicts if it is able to know what's the Fiat-Shamir randomness, the Fiat-Shamir value that's derived for R, that turns out to help you a lot. So that's sort of what we're going to try to do. So we'd like our circuit C star. It gets as input a witness W. It does some stuff. I'm not sure yet what. But eventually, it's going to try to predict what's our Fiat-Shamir randomness. So what is our Fiat-Shamir randomness? Remember this point R. How was it derived? We hashed everything we knew at the time, which is the circuit digest of C star. It's the claimed output Y star, again, just 0, 0, and some hash alpha of some witness. All right, so this is what we are trying for our circuit to derive in order to predict the Fiat-Shamir randomness. This turns out to actually be a problem because in order to write down this circuit, I need to know its digest. Right, so to describe the circuit, I need to already know how the circuit operates, what its digest is. So there's a circularity here, and it's not clear how to do something like this. The way we'll get around the circularity is by having we'll pass along this digest as a witness to the circuit. Okay, so what do I mean by that? So here's the actual circuit for which we mount our attack. So it gets as input a witness W. It's going to sneakily think that this W is actually a digest of its own description, but that's what it thinks. It doesn't have to be the case. So we interpret W as some circuit digest psi. We'll treat we now kind of sort of follow the honest strategy, which is compute the PCS hash of the witness W. And now when we try to compute the Fiat-Shamir hash, instead of plugging in like this bracket C star, which we cannot, we plug in psi. We put in Y star, again 0, 0, and this value alpha that we just predicted. This gives us a value gamma, which we're going to treat as a candidate value for R. Okay? And now we do something which will be mysterious at this point. We'll clarify it in a bit. We output the string gamma and gamma minus 1. It shouldn't be clear yet why we do it, but that's what we do. Okay, remember our circuit, or I should say, the circuit is a circuit that always outputs 2 feed elements. And my claim is that it never outputs the value 0, 0. Indeed, this is the next thing I want to claim. The circuit never, ever, ever outputs 0, 0. Do you see why? Well, it always outputs 2 distinct feed elements because you subtracted 1. Okay, so this claim is certainly true, and not hard to prove. The more interesting thing I want to show you is how to produce a proof that will actually convince our verifier to accept this claim. Say, oh, you know what? There is some W that makes the circuit output 0, 0, although we agree that there does not. Right? Okay. So this is what I want to show you. So what does a cheating prover, need to describe what the cheating prover does. So first thing the cheating prover does is need to say, what circuit am I using? Well, we'll use obviously the C star that I just told you about. The next thing I need to do in the attack is tell you, what is the claimed output Y star, 0, 0. And I also need to give you a PCS hash of the witness. So I pass along the PCS of the circuit digest of C star, which now I know. So that's what I do in the first step. At this point, if you think back about the protocol, we start running GKR and do all this stuff. But let's pause here for a moment and think what happens at this point. Okay? So the actual output of the circuit is what, we just saw what the circuit is. It's going to output this gamma minus 1. And I want, which were derived in some way. We'll recall in a second. But just think for a moment about this gamma minus 1. And I want to ask you a simple algebra question. So what is the multilinear extension of a polynomial that, say, at 0 gets the value gamma, and at 1 gets the value gamma minus 1? So you can just think here of actually, because we're talking about a multilinear polynomial, but because the truth table of size 1, it's essentially just a linear function. So the multilinear now is just 1. So take my word for that. And what we're looking for is a linear function that at the point 0 outputs gamma, and at the point 1 outputs gamma minus 1. So what does it output at the point 2? Gamma minus 2, right? It's a line. right? It's a linear function. It's a line. If it's 0, it outputs gamma. At 1, it outputs gamma minus 1. At 2, it outputs gamma minus 2. What is it that output at the point r? Gamma minus r, right? Good. So now let's go back and recall what is gamma and what is r. Well, gamma, we had this construction of the circuit. It's the Fiat-Shamir hash of the circuit digest, y star, and alpha, right? That's how we constructed the circuit. What is r? R was derived by applying Fiat-Shamir. How do we apply Fiat-Shamir? We hash the circuit digest, y star, and alpha. Oh, and they happen to be the same, which tells us that the multilinear extension of the real output of the circuit at the specific point r is equal to 0. So far, so good? Cool. So that's the real output of the circuit. What about the false output, the one that I'm trying to convince you of? So the output 0, 0, what happens with that? So now another fun algebraic fact. What is the multilinear, or rather linear here, extension of the function that at the point 0 outputs 0, at the point 1 outputs 0? What is the output at the point 2? 0. What is the output at the point r? Also 0. It's always 0, right? So what we see here is that the multilinear extensions of both the real output and the fake output of the circuit agree actually on the point r. It's kind of these two functions, the 0 function and the gamma minus r function, or gamma minus x function. So we started off with the false claim that the circuit outputs the value 0, 0. But when we apply this Fiat-Shamir step, we've switched over to a claim which is actually true for the circuit. The claim that this circuit, if you take its extension, the extension of the output, and evaluate it at the point r, you'll see a 0. It's a correct claim. So from here on, now, since we have a correct claim, we can just run the honest prover strategy, right? We can just keep running the GKR honest prover strategy, the honest PCS evaluation proof, and convince our verifier. Right? The key point is that we've shifted over from a false claim to a true claim. And once we are in a true claim, game over. Okay? So just to see pictorially, how does that attack work? Well, the prover specifies the circuit C star. It sends over the claim that the output is 0, 0, and it sends over alpha. This should be PCS of the digest of C star. The verifier, follows Fiat-Shamir. It sets R to be this hash value. And what we just saw is that the claim that it's now trying to verify, the claim is that y star hat at R is equal to 0, is actually true with respect to the true claim. So from here on, we just run the honest GKR protocol and the honest PCS eval, and our verifier accepts always. Okay, so going back to this question, is our circuit C star contrived? At first glance, it seems a little bit weird because it does this like PCS evaluation and it does the Fiat-Shamir hash. And why would someone ever want such a weird circuit? Well, it turns out that we want such circuits. In particular, circuits that evaluate hashes are extremely popular. So for example, if you want to check things like is some value a hash of a database or blockchain or whatever that satisfies a value. Or I think even more concerning, when we apply recursive proof composition, we're inherently trying to prove things about the Fiat-Shamir hash of the outer proof system. Okay, so circuits that contain the Fiat-Shamir hash are actually widely used in practice. So I think this attack is concerning. Okay, so we have this attack, and I mean, it's a problem, and we're going to discuss it more. But what about, we would like for this attack to go away, and it's not clear that it can, but I want to point out kind of two lines of work. So first of all, there's been a lot of work actually in the theory literature, and things I've been involved with also, about showing sort of provably instantiating Fiat-Shamir in the plane model, using explicit hash functions based on nice cryptographic assumptions like LWE, DDH, and so on. So we have a lot of work on this. We've made tremendous progress in recent years. The caveat, though, is that, first of all, what we have so far will not give you full-fledged snarks. You can get very meaningful notions, but not snarks yet. And secondly, they are very far from being practical. In particular, they're using, or much further from being practical as compared to just hash functions, they use machinery like FHE and so on. Still, having said that, we could have had the same criticism about things like zero knowledge years ago and about FHE years ago. So this line of work, I hope it makes progress, and that eventually we'll be able to just prove soundness. Still, we need something for today. So let me mention some mitigations against the attack. So these are ways to change the protocol, let's say, in a way that I don't know how to mount the attack. So a key point, and we'll hear more about it later today, I think both from Elon and when we'll chat. A key point in this attack and all of the contrived attacks before, it's really crucial that the circuit is able to evaluate the Fiat-Shamir hash. Right? And some way to get around this might be to try to make sure that the circuit is unable to evaluate the Fiat-Shamir hash. So mitigation that we suggested in the paper is to increase the depth of the Fiat-Shamir hash function to be larger than the depth of the circuit being proved. And this is this fix that's used by Expander. A second proposal from this really interesting new work by Gal Arnon and Elon, and Elon will talk about it, I think, immediately after me. Elon will tell you about it more, but they're increasing the size of the hash function. And to make it actually work, they're using a really cool proof of work idea. Elon will tell you more about it, and we'll discuss it. Something interesting is that they also show that their protocol is secure in a new idealized model that they introduce and is sort of geared at sort of capturing these sort of attacks that we have, but it doesn't quite capture all of the attacks. And in particular, for technical reason, doesn't capture our attack. But we'll probably talk about that more. So let me just kind of conclude. What we showed in this paper is that actually the random oracle methodology can fail in a practical scenario, which I think is quite concerning. Let me just end with a couple of open questions. So, I think one immediate reaction after seeing this attack is to think of sort of easy fixes which make it not apply. I think it's not hard to do stuff like that. The more interesting thing is, as cryptographers, we're not happy just that there is no attack. We'd like some sort of evidence for security. Elon and Gal have a work in this direction, but I'm hoping to see more of that. I also, going back to the beginning of the talk, really encourage you to try to prove false statements. I think, these ideas are kind of new, and I think there's a lot of potential to extend them. So you're very encouraged to do so. A particular challenge, which I think will be, if you can do it, I think it would be very dramatic, is to be able to get around, say, R mitigation. If you can get around R mitigation, you'll be able to break a lot of stuff. So if you can break Fiat-Shamir when the circuit is more shallow than the hash function. And yeah, if you can do practical attacks, attack the GGM. I think I don't have time to go into it. If you're interested, I can tell you more about that as well. So I think I'll end here. I'm not sure if I have time for questions, or we'll keep them for later.
We'll coalesce the questions with the panel.
Absolutely.
Thank you so much.
Sure.